Okay, good evening, everybody. We're going to start the Chemistry Additional Science Section 2 Hangout. I hope you enjoy it. It's a new chance for us to show off some technology to hopefully engage with you at home, and it should be a relatively useful way for you to find out some key tips for the exams coming up. And I'm going to go through a couple of basic points with you. First of all, there's going to be 3 or 4 questions as we go along. If you do have a pen and a paper and a calculator handy, I really would recommend you trying to answer the questions as we go through. I'll give you a little bit of time to do that. Secondly, as we go along, please feel free at any point just to comment. They're not visible comments. They come straight directly through to me, so other people won't be able to see them. I will pass on good comments, but I will not post your name, so you're very welcome to ask any questions you've got, and if they're relevant and useful, I'll do my best to answer them and pass them on. Alternatively, you might just fancy passively listening into this and checking your understanding with only a few weeks to go before the exams. Finally, when these are complete, we will save this YouTube video and you'll be very welcome to access it at any time if I've gone a bit too quickly, if there's something you've missed out. On top of all of that, please feel free to come and ask me any questions at any point via email, via comments, and we'll try and get back to you in aid of your prep. For those people using the Frog website for comments, there is one small issue at the moment. The comments will not auto update. So if you have a look just to the side here, there is a little refresh button. If you click that every 5 minutes or so, you'll be able to see any of your comments that I've answered, but hopefully I'll try to answer them in person as we go through. So I hope you find it useful. We're just going to now move on to the next part of the PowerPoint as we begin. And we're going to be looking for this first part about the key topics. Now, the exam's only a few weeks away, and there are some relatively large points that we need to cover. And unfortunately, I don't think we're going to get through all of them in the hour. So on this first session, we plan to look at the following. We're going to look at atoms, specifically ionic, covalent, and metallic bonding. We're then going to look into new materials, alloys, and polymers. The tougher one, the one where I'm going to ask you to use your calculators and a piece of paper, the chemical calculations. One of those ones where doing a few examples will hopefully make it clear how we get to the answers. And then finally, for today's session, we'll look at chemical analysis, human versus instrumental. But I'm going to start before all of that on our first key bit, data sheets. In your exam, you're going to be given a data sheet, and it looks like this. And it comes in 2 parts. There's a front page and the periodic table, the side page. And I think at that point, it's quite important for us to go through why they are included and of what use you can make from them. So first of all, the chemistry data sheet. Well, this shows us 2 things. The first section is the reactivity series of metals. It shows you how reactive a metal is, from our very, very highly reactive metals, such as potassium, sodium, calcium, down to our very unreactive metals, such as gold and platinum. Now, this becomes really important when we start looking at ways that we can utilize these metals, and more specifically, how we actually get the metals from the ground, be that a displacement reaction or be that electrolysis. We'll go into these in more detail in the next PowerPoint, but the key thing for you to look at this point are the 2 exceptions, carbon and hydrogen. Now, these aren't metals, but they're in there because they're very, very useful, mainly because they are cheap. And so carbon is able to displace anything below it. In other words, it can purify these materials below, these elements, but it can't do anything for the ones above it. And this is why we can determine how we get our metals, be it electrolysis or be it displacement. We'll come on to this in more detail later on. The second part, which we'll look at today on our data sheet, are the common ions. Now, when our atoms react, we might find that they form ions. And these are very, very useful things to know. Well, notice a couple of things with this. Sometimes our metals will end up losing electrons. And based upon the amount of electrons they lose, they'll be given a charge. Well, our data sheet tells us the common ions. So sodium, for example, is Na+. It's a single plus, meaning a single electron has gone somewhere. Second example, such as magnesium, is Mg+2, which means it has lost 2 electrons. And furthermore, if we look at things like chlorine or oxygen, the oxides, the chlorides and the oxides, have gained a specific number of electrons. So chlorine is a negative. In other words, it's gained 1 electron, whilst our oxide is 2 negative. Again, meaning it has gained 2 electrons. Again, we'll come back to all of this later, but it's really important that you have that data sheet handy, because these bits of information are really clear and really important for when we're balancing equations and looking at half equations, and even potentially looking at the processes of electrolysis. The next part for this on our data sheet is the periodic table. And again, it's got a huge amount of information on it. First of all, we've got our groups. So group 1, group 2, going down here, and group 7, and group 0 or group 8 going down here, and all the ones in between. Well, this tells us lots of really important information on the periodic table, and again, we'll use this a lot as we look through. But essentially, if we've got elements in group 1, they have 1 outer electron. If we have elements in group 7, they have 7 outer electrons. And this will give us really important clues for when we come to look at the bonding and the equations. Finally, though, on the data sheet, 2 parts. If we find something in group 1, for example, the alkali metals, they all have very, very similar properties. Likewise, anything in group 7 all have very similar properties to one another. So the periodic table gives us lots and lots of key information. But probably the most important part is this, the key. Because on it, it will tell us 2 things. It will tell us the relative atomic mass, and it will also tell us the atomic number. Now, the atomic number is at the bottom, and the atomic mass is at the top. We'll look at this in more detail in a minute, but always refer to this in your exam. For when you're talking about atomic bonding, when you're looking at electron structures, these will give us the clues about where it should be, how many electrons it should have in its outer shell, and the absolute mass of particular things that we are looking at, from carbon to all the different elements in the periodic table. So let's begin. The very first topic that we're going to look at is the atoms. We're going to look at atomic mass, atomic number, and a phrase called isotopes. Now, this is an extremely common set of questions. This will be coming up in your exam. So learn the basics of this, and you're bound to get at least 4 or 5 easy marks right at the beginning. So the first point we're going to look at is a simple fact, some knowledge that you need to learn. And it's this. The subatomic particles have a given mass. You simply need to know it. The protons and neutrons are large. They've got a relative atomic mass of 1. The electrons, on the other hand, are extremely small. We say very small. In the exam, you'd get away with saying that they are 0, or they are 1/2000th, or simply they're small. So there's our first fact that we need to learn from this part, that the atoms, the subatomic particles within them, the protons, the neutrons, and the electrons, have their own given masses. Now, specifically for the additional science exam, you're going to need to be able to know how to use the mass number and how to use the atomic number. Well, the atomic number is very clearly our number of protons. It's what makes each element its own element. So, for example, hydrogen has an atomic number of 1. Anything with an atomic number of 1 will only ever be hydrogen. And conversely, carbon, an atomic number of 6. It is carbon. So the atomic number is the number of protons, the number of positive protons. Now, for core science, that number of protons will also equal the number of electrons, because atoms have no charge. They have no overall charge. And so if you look at something like sodium, which has 11 protons, if there are 11 positive things, for something to have no charge, there must be, by definition, 11 negative things, because they cancel one another out. Now, that doesn't really come up in the additional science part, but it's a good bit of information to know in the background. The second part to all of this is the atomic mass. Now, that's the number of protons and neutrons added together. It's essentially the molecular weight of our element. And so hydrogen has an atomic mass of 1. It's very small. In fact, it is the lightest element there is in terms of its mass. But something like sodium has an atomic mass of 23, much bigger. So the atomic mass and the atomic number are shown on our periodic table. And again, in the exam, use that. It's really important that you can refer to this to check your numbers. So that's atomic number and atomic mass. The atomic number, the number of protons. The atomic mass, the number of protons and the number of neutrons, given our overall weight. Now, for additional science, there's one further thing we need to know. And this is a word called isotopes. Now, an isotope is exactly the same element. It's got the same number of protons, the same atomic number. So it is always going to be the same element. And because it's got the same number of protons, it also has the same number of electrons. The biggest difference, however, and the reason we call it an isotope, is because they are heavier and they have a different number of neutrons. So we have ourselves our classic carbon. And carbon can come in 2 forms. It can be carbon 12, or it can be carbon 14. There's no difference between the two. They are both carbon. But carbon 14 has 2 extra neutrons in it. And those 2 extra neutrons make it heavy. They make it unstable. They are likely to decay. They are likely to be radioactive. And we'll talk about that more in the physics module when we come to it. The next part to the atoms, which now gets a little bit tougher, is bonding. There are 3 types of bonding. The first that we're going to look at is our ionic bonding. Now, ionic bonding is our transferring of electrons. Electrons are moving somewhere from one place to another. And when they do that, we get a bond that is very, very strong. You're going to need to, in the exam, talk about how this happens and what you find. Now, in the exam, you'll be able to simply draw the outermost electron shell. So I'm going to take an example. I'm going to take something like sodium. I do apologise for my terrible drawing on screen, but hopefully you get the point. Here's my sodium. This is my furthest outer electron shell. And if I have a look, I find sodium in my periodic table is here. It's in group 1. So I know there is one outer electron. If it was in group 2, I'd be drawing 2. In group 3, 3, etc., etc., etc. Group 1 tells me I have one outer electron. Now, if I put that near to another element, for example, chlorine, if I look at my periodic table, is in group 7. It's got 7 outer electrons. 1, 2, 3, 4, 5, 6, 7. Now, if you remember in core science, the elements want to gain full outer shells. They want to become stable. And they fill up the electron shells in an order at GCSE of 2, 8, 8. So in this example, sodium desperately wants to lose an electron, whilst chlorine is eager to gain an electron itself. And so if you bring sodium and chlorine together, one of the electrons will move across. This will go down to its previous most complete outer shell, having lost this electron shell. And the chlorine here would have gained. And so we've actually formed ourselves a very strong bond, an ionic bond. Very technically, this sodium has gained a positive charge because it's lost a negative electron. It's lost something negative. It's become positive. And conversely, the chlorine has gained an extra electron, so it becomes negative. Now, with that in mind, we end up getting the following. We get ourselves structures that look like this. We call them lattices. In fact, they're a giant ionic lattice. They're arranged very regularly with positive and negative charges, and they have extremely strong electrostatic forces. They really bind together in a strong way. Finally, we normally find that they're cuboid. They form crystalline shapes, held together extremely strongly. And because of that bonding, because of the positive and negative charges all the way through, we find that ionic bonds, in fact, ionic compounds, have very, very high points, very, very high melting points. They also have very, very high boiling points. If I could spell, do apologise. And so they are very, very difficult to melt. Now, in terms of exam questions, what are you likely to be asked? Well, 2 parts. First of all, you're likely to be asked a little bit about the type of bonding in ionic bonding, i.e. the melting points, the boiling points. Are they able to pass electricity when molten? But furthermore, you're probably going to have to actually draw some electronic structures of the ions. Well, before we get into these, I'll take you back to this diagram. This is just like I showed you earlier on the data sheet. It shows us the common ions that we are going to have. And so we know that lithium will have a positive ion it will lose 1 electron. And conversely, something like fluorine will gain 1 electron. And again, we know all of this because we look at what groups they're in. If they're in group 1, they're losing 1. Group 2 are losing 2. And conversely, group 6 will be gaining 2. Group 7 will be gaining 1. It's all about getting the full outer shell. But specifically with that, the marks for you in your exam will come from actually showing some ionic bonding. Now, you won't need to draw the full atom unless it tells you. Normally, you can get away with simply drawing the final outer shell. And so I'll show you a couple of examples and talk you through how you get your marks. Let's take sodium chloride. When we bond sodium chloride, we find the following. We've got ourselves some sodium. And if I looked at sodium, I would find that it was in group 1. So I would have 1 outer electron. And if that went near some chlorine, chlorine is in group 7, it has 7 outer electrons. When they go together, I'm going to find that this electron will go over here. But to get the marks, you'll need to draw the before and after. And there's one quite specific rule that you need to follow. You're going to need to draw where we were in outer shells before and where we are in outer shells after. So sodium has lost its outer electron. So that whole electron shell goes, and we go back to the previous electron shell, in which case it's a full electron shell. Now, you won't need to do this in the exam, but to be complete, we would actually have a first shell in sodium, which has 2 electrons. Again, remembering 2, 8, 8. And if we look at our chlorine can still keep the same outer shell as before with our 7. Hopefully you'll be a little neater than I. But now what we can do is we can draw the electron that moved. To get our marks, we've got one final thing to do. We need to draw brackets around each. So here is our sodium chloride, and here comes the final mark. The sodium has lost a negative electron. It's lost something negative, so it gets a positive charge. Whilst our chlorine has gained that negative, so it becomes negative. I'll give one quick example again, and I'll rush through this one a little bit quicker. But again, if I took something like magnesium, now magnesium, again, apologies for my drawing, is in group 2. So I've got myself 2 outer electrons. If magnesium were to go near something such as oxygen, which is in group 6, it's got 2 spaces. I'm going to find that these 2 electrons will move over into these 2 places. And so to draw it, I would drop back to my magnesium previous shell with 8 in total. And I would go to my oxygen. I can draw the same outer shell. But now the oxygen has got 2 of the electrons. And so when I draw my bracket around it, I have my magnesium, which has lost 2 negative things, so it becomes positive 2. And my oxygen has gained 2 negative things, electrons, so it becomes negative 2. And that's the electronic structure of ions. Hopefully, Everyone is okay with that. The rules here, please look at the grouping, please look at the charges, and remember the brackets. We're going to do two more parts now to bonding. This one's a little bit quicker. This is covalent bonding. Now, covalent bonding is sharing of electrons. Now, in covalent bonding, we don't actually lose the electrons from one place to the other. But what happens is the electrons essentially share the outermost electronic ring structure. They cross each other's paths. Let me give you an example. Here's hydrogen. It's got one electron. It needs to gain another electron from somewhere to complete its outer shell. In the hydrogen, it's only got one shell, so it only needs two to fill. Now, if it goes near another hydrogen atom, what we find is that actually the electrons cross one another. So this hydrogen here on the left thinks it's got this dot and cross. It thinks it's happy. And this hydrogen over here also thinks it's got the dot and the cross. So it thinks it's happy. And so covalent bonding is simply the sharing of electrons in the highest energy shell. Now, there's lots of different examples, and I won't go through all of them, but I will give you a relatively complicated one. And this is something like methane. So if I take methane, which is carbon, and carbon has 4 outer electrons. Now, for carbon, if it goes near hydrogen, it will form CH4. 4 hydrogens can go near it, and they can share their individual electrons, and everyone is happy. This hydrogen here thinks it's got 2 electrons. This hydrogen here thinks it's got 2. This one here and this one here. And most importantly, the carbon thinks it's got a complete set of 8. So that's covalent bonding. It's for sharing of electrons. Finally, with covalent bonding, there are a couple of things that you need to be aware of. First of all, in covalent bonding, the forces are incredibly strong. If you get 2 chlorine atoms near one another, very difficult to break them apart. But actually, when they form molecules, the forces between the molecules are actually quite weak. So for example, if you've got lots of oxygen all together, splitting the actual oxygen molecule is quite easy, because the forces that hold the 2 oxygens or the 3 oxygens together are quite easily pulled apart. The sharing of the electrons, i.e. the fact that it is O2, is more difficult to break, but simply splitting the intermolecular forces is quite easy. And so in simple molecular covalently bonded substances, they have very low melting and boiling points. They also are unable to conduct electricity. There's no ions, no electrical charge. Now, for your exam, these 3 diagrams are crucial. It's crucial you learn their image. We have ourselves diamond. We have ourselves graphite. Apologies for my writing. And we have ourselves silica. Now, the important part for these is we call them giant covalent. They are very big molecules. Now, they're all bonded by very, very strong covalent bonds. So if we look at something like diamond, each carbon is bound to 4 other things everywhere. And it makes it extremely hard and very difficult to boil and very difficult to melt. And so you need for your exam to recognize these 3 giant covalent structures, make sure that you can name them, and be aware they are very strong and they are very difficult to melt. Now, the final part to all of this is our metallic bonding. Now, metallic bonding is the bonding that happens between metals. Now, the specific part that you need to know in the exam for this part is that in metallic bonding, we get ourselves lots of free electrons. We call it a sea of delocalized electrons. What that means is the electrons can move. They can whiz about all over the place. And in doing so, these free electrons are able to conduct both heat and electricity. So metallic bonding is our simplest part. It's able to conduct heat and electricity because of the electrons which are able to move fluidly throughout. Right, ladies and gentlemen, I've spoken quite a lot now, so let's have a very quick look at our first exam question. This is an exam question on atoms, and this is the point where I'd like you to have a very quick look at it yourself with a pen, a calculator if necessary, and on a piece of paper. And let's go through it. I'll highlight some key things as you're looking through, and this is what I expect you to do in your exam. What are the key bits? You'll notice in the corner of these exam questions, I'm going to have a countdown timer. Now, I'm going to be a little bit mean, as I normally do for those of you that remember who I've taught. I tend to talk a lot. So I'm going to go a little bit quicker on this part, but I'd say a minute or so to answer this question, and then we'll go through it. If I was doing this exam, I'll be looking at the following, and these are all taken from previous exam questions across all the boards over the last few years. And this is the type of question that the exam will have. So they're giving us this substance, ammonia. We don't need to really know what it is, but they've given us a formula, NH3, and they've drawn us the 2 atoms. The diagrams show how electrons are arranged in nitrogen and hydrogen atoms. Draw a diagram to show how the electrons are arranged in ammonia molecule. The important bit, you only need to show the highest energy level. And when you've done that, the question, explain why ammonia has a low boiling point. They tell you it's a gas at room temperature. Finally, when you're in the exam, please look at this. How many marks are they awarding you? 2. Well, hopefully that's about enough time for you to have a good stab at this question. I'm going to start the answer now. If you're looking at this not live, you're very welcome to pause and try and answer and go through yourself. Well, the first thing to look at here is we know that the formula is NH3. So I'm going to have an N, and I'm going to have myself 3 hydrogens. Now, nitrogen will have in it 4 outer electrons. I know that because they've drawn it for me already. But again, 5. But I could look on my periodic table to check what group it is in. And so if, like me, under the pressure, you've made a very simple mistake and you're about to draw 4, go and check yourself on the periodic table, what have I got? Nitrogen in group 5. So I'm going to draw my 5 electrons. 1, 2, 3, 4, 5. And now, next to it, hydrogen in group 1 with 1 outer electron. And again, I'll just check, and there it is. Well, there are, for each of my hydrogens, the single electron. How do I know this works? Well, nitrogen now has a total of 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen has a full outer shell. Each hydrogen only has 2. So that is how I would draw my ammonia molecule. Now, if I was going to answer the question specifically about why ammonia has a low boiling point, for 2 marks, I'll be saying 2 points. First of all, I would be saying it is small. It's a small molecule, or it's simple. It's got a simple molecular structure. Do apologise for my writing. The second mark is going to come from the fact that it has weak forces between the molecules. Remember, it's a covalent bond, and they are weak. It's quite easy to prize them apart. Okay, question 2. It's the last question for this first part. Question 2 is as follows. And I'm very sorry, I've made this quite small here, so I will read this part out. This was, in the real exam, a bigger question. You would have seen this in better detail. It says the following. The picture shows sodium reacting with chlorine. The reaction forms sodium chloride, which contains sodium ions and chloride ions. And I've just started the timer as we go through this. The diagram shows how electrons are arranged in sodium and chlorine atoms. Explain in terms of electrons what happens when sodium reacts with chlorine. It's worth 3 marks. They've given you a clue. For those of you who can't see it particularly clearly, I've got 1 outer electron, and I'm going to look at my periodic table and check that sodium, Na, is in group 1, which it is. And I'm going to look at chlorine, and chlorine's in group 7, 2, 4, 6, 7. When you've looked at that, you then need to explain as fully as you can why sodium chloride has a high melting point. Now I'm going to give you 1 minute or so for this while I check the comments to check that no one's asking for anything specific, and that you can still hear me and I'm not going too quickly. Okay, so I've got a question that's asking me, do we draw dot and cross diagrams like that in the exam? Yes, we do. Welcome to a few people. Goodness me, we've got quite a few people on here, which is great. Dr. Fellis has just informed me that it would appear that earlier on, it did seem to crash for her, but she refreshed and is back straight in with us. This will be saved as a complete program. So if you have found a few technical issues, I'm really sorry. It's the first time we're trying it, but it should now be up and running, and it has been saved regardless. So we can look at it at a further time. Okay, 3 marks here. Explain in terms of electrons what happens when sodium reacts with chlorine. Well, our first mark is going to come from saying that sodium is going to lose an electron. It's going to transfer it. So that gets us our first mark. Our second mark is going to say chlorine is going to gain the electron. It will take it. Finally, for our third mark, this is all going to be happening in the outermost electron shell. Nothing is going to be happening in the shells previous. These will all stay the same. These will all stay the same. Purely the outermost one. And so the marks were in the picture. Always look back. Always check that it's there. For part B, we're now explaining why sodium chloride has a high melting point. Well, 3 specific marks here. First of all, you'll get a mark for saying it was a lattice. It's a giant lattice. It's got positive and negative charges all the way through, all these ions. The second mark would be saying that the forces are strong. The electrostatic forces are very, very strong. And finally, it's then linking that. If the forces are strong because of the positive and negative ions holding one another together, you're going to need lots of energy to melt it. And that's where the 3 marks come. Okay, ladies and gentlemen, that is the first part of atoms. Alloys is a little bit quicker. Alloys for me is part 2, and it's a question that comes up most years. It's just a couple of factual questions, of factual points that we need to learn. And we're going to look specifically about lots of new materials. So smart materials, polymers, alloys. Now, I was always told by a previous colleague of mine that the reason the Romans were so good at fighting was because they were some of the first people to have alloy swords and shields. Now, whether or not that's factually correct about the Romans, I'm not sure. But the fact that you have alloys, well, an alloy has something with different properties. Specifically, it might be lighter. It might be stronger. It might need more temperature before it melts. I always think of something on a car, an alloy wheel. That's meant to be a car. Goodness me, my drawings never got better. They're shiny, they're strong. There's something about them. Specifically for your exam question, why? Why are alloys stronger? Well, if you have a look on the left-hand side here, this is a normal metal, a normal element. It's got uniform particles. The atoms are all the same. And so they can slide over each other very easily. And so there's not much strength to them. You can easily push or move them. But with an alloy is a metal that is added with something else. It could be another metal, but it could actually be other elements. The key bit with it, though, are these bits. The atoms are different sizes. And so what we find is the smaller atoms, or the larger, it doesn't really matter which, but they get in the way, they get stuck, they stop the atoms from moving freely across. And so it makes them very, very strong, or it gives them different properties. So an alloy is a mixture of materials of which one is at least a metal, and it gives them properties normally stronger or harder or higher boiling points and melting points or lighter. The second part to our new materials are smart materials. Now, smart materials have some very strange properties. The one that I would remember specifically are things that we get braces out of. These are things like nitinol. It's a metal that keeps smart properties. And what I mean by that is as follows. It's a very strange metal that if you warm it, it remembers its shape. And if it goes cold, it will suddenly become flexible. And that's why we have them as braces. They're cooled down and attached to someone's mouth. But as they warm inside your mouth, they begin to find their shape again. And in the case of braces, they begin to pull. And so what will happen is your teeth will be straightened because the nitinol, when it's warm inside your mouth, is trying to return to its shape. So for the exam, a smart material is something that will keep its shape or return to its shape when heated. The second part to all of that is this word nanoparticle. Now, all you really need to know for nanoparticles is that they are very, very small, 1 to 100th of a nanometer. To give you some kind of context, that's a billionth of a meter, incredibly tiny. We use them for lots and lots of different purposes. So it could be things like carbon nanotubes, very, very strong, very, very small. And we're thinking about one day using them as space ladders, incredibly strong materials. We use them nowadays for reinforcing tennis rackets. But we also have nanoparticles in everyday things that we use, like sun cream or deodorant. Now, the sun cream and the deodorant have the nanoparticles that do exactly the same job as previous sun creams and previous deodorants, but they're tiny. So you don't leave a white mark. If you've ever sprayed deodorant and you've worn something black, previous deodorants, old-fashioned ones, would have left a very, very fine white powder all over it. And the same with sun cream. Well, the nanoparticles avoid that. Finally, on our new materials comes polymers. Now, polymers is always a very difficult exam question because there are so many different types of polymer. It's very difficult to know what they're going to ask you. 2 rules. First of all, there can be 2 types of polymer. The first is our thermo-softening. I'll come on to what that means in a second. The second one is thermo-setting. Now, the difference is that with heat, one can melt again, thermo-softening, whilst the other is constantly set. So, for example, if you've ever played rugby, you've probably put in a gum shield. This is a thermo-softening product. You put it in your hot cup of water and it will become very, very flexible. You then let it cool a little bit, put it in your mouth, press it up against your gum, and it will bond to your teeth. It will then set rigidly. However, if you knock some teeth out or your teeth change, you can put it back into that hot water and it will remelt. It does that because it's thermo-softening. If you look closely, there are no crosslinks. The strands can easily break. The flip side of that is a thermo-setting polymer. Something like the kettle itself, or a plastic plug, or a laptop case, something that you don't want to get hot and melt. So you heat these once and they're in their place forever because they have crosslinks. They are stuck rigidly. Now, with your exam question, I wish I could give you some guidance here, but I'm not really sure what they're going to ask. I can guarantee you they will ask something on polymers or alloys or smart materials. They always ask one of those questions, but specifically, what are they going to ask you about the plastic? I don't know. And this is why this picture is here. They will ask you particular questions about a plastic. It might be something like a plastic bag. Why would you use it? What properties would you want? Well, for a plastic bag, you might want it to be transparent. You might want it to be very, very low in cost. You might want it to be flexible. If you flip that and you go for a car bumper, well, actually, you might be less worried about the cost, but you might want it to be very, very rigid. In other words, take your time. Look at the questions they're asking, look at the properties they give you, and go from there. Ladies and gentlemen, we're at part 2 now. I'm going to be relatively quick on this because I do want to finish on the calculations. So, exam question 3. We've got a picture of a sword. It's about 3,400 years old. It's made of an alloy of bronze. They then tell you that bronze is made from copper and tin. Look what I'm doing. You should be doing this in your exam. Highlight the key bits. Tin is pretty important. That's what bronze is made out of, copper and tin. It's going to come in useful in a minute. They're then saying bronze made better swords than pure copper. Bronze is harder. Why is bronze harder than pure copper? And then for 4 marks, you're asking about why in terms of arrangement, why is copper soft, and why is copper hard? When you've done that particular bit, we then have a question on a drinks bottle, which is thermo-softening. It can be recycled. The question, how is the plastic bottles changed into new plastic objects? How do they recycle that? Okay, let's have a look at this question. For 4 marks, we should be answering the following points. Let's start with copper. Copper, for 1 mark, is arranged in layers. The atoms can slide over one another very easily. And in doing so, the fact that they can slide makes it soft. So copper in layers for 1 mark, able to slide, and soft for our second. For bronze, it's got tin in it. It's not pure. So these are my copper atoms, but I'd have some smaller or bigger, it doesn't really matter what we draw, but some other atoms which have a tin. It's our alloy. And so bronze cannot slide. Those atoms cannot move. The tin atoms disrupt or distort. And so if we can't slide, it's a harder actual product. On the second question, well, thermo-softening is our clue. Essentially, if we give ourselves a bit of heat, we're going to melt the plastic. There's 1 mark, thermo-softening. You can then mold it or shape it into what you now want. There's your second mark. We can do that because it's thermo-soft. There are no crosslinks, or the polymer chains or molecules have weak intermolecular forces. The forces are weak. Finally, because they're weak, because there's no crosslinks, we can melt when heated. 2 more parts, ladies and gentlemen. Very quickly, question 4. We've got ourselves on question 4, graphite and diamond. They are formed from the element carbon, but they've got very different properties, and they give us our structure for both. 4 marks as to why. Now, I'm going to give the answer quickly because I'm a little bit worried of time, but if you're watching this post live, you might want to pause it and see if you can answer it. But it's a similar kind of answer to our previous question. The graphite doesn't have any crosslinks. And so the graphite, the layers are able to move between the layers. And that is because the forces are weak. So graphite is not very strong. Well, the opposite is true for diamond. Every carbon is stuck to 4 others. There are crosslinks everywhere. It's incredibly rigid. 4 bonds for every carbon. And so the fact that they cannot slide means it's very hard. Finally, graphite can conduct, but diamond cannot. Think about what we need to conduct. We must have electrons that can move. I used a phrase earlier, d localized electrons. A sea of electrons. These electrons can move, and if they move, they carry current. And in doing so, they pass electricity. Diamond does not have any electrons that can move, and so it cannot carry any charge. Okay, ladies and gentlemen, we're into the last part of this particular presentation. We will go into more detail later on later presentations. It will go in the stuff that we haven't quite had time to go through today, because I'm very conscious you do have a triple science class after this one. We're just now going to quickly look at chemical calculations. Relative atomic or relative formula mass is where we're going to begin. And this is something that often scares people. It looks relatively confusing, but again, the clue is what they're going to give you in the exam. Because in the exam, you have your periodic table. And in there, we are given our atomic masses. So, relative atomic mass. Well, that is simply saying how heavy different atoms are compared with others. And the classic one we look at is carbon-12. Let me give you that example. Let's take some relative atomic masses of some different products. So if I have a look at hydrogen, hydrogen's got a mass of 1. Carbon, a mass of 12. And so I would need 12 times the amount of hydrogen to molecularly weigh the same as carbon. So relative atomic mass is very simple. It's on the periodic table, the relative atomic mass is given. It's very unlikely they're going to ask you that in the question papers. They're probably going to ask you formula mass. But again, we use our periodic table to give us our answers. And I've been lazy, I've planned ahead here. On the board, and again, if you're watching non-live, you might want to pause it at this point and see if you can work out the formula masses. I'll do the first one for us. I've taken the relative atomic mass of all the elements that I'm using, and I've just drawn them here so I can quickly get to them without looking up. So let's work it out. Let's start with hydrogen. Well, hydrogen has got a relative atomic mass of 1, but I've got 2 of them. So the formula mass would be 1 times 2. The answer would be 2. See if you can be going through the others. And again, I apologize. I'm going to go relatively quickly, but you might want to pause this and try. Calcium, relative atomic mass, 40. Carbon, relative atomic mass, 12. Oxygen, relative atomic mass, 16. But I've got 3 of them. The digit goes back to the element before. So I need to multiply that by 3. So 40 plus 12 plus 16 times 3, or 16 times 3 is 48, plus my 12 is 60, plus my 40, I have an atomic relative formula mass of 100. If we go back, hydrogen weighs 1, but there's 2 of them, plus my 16 for my oxygen. Nitrogen weighs 14, hydrogen weighs 1, but there's 3 of them. So that is 17, that is 18. We've already done hydrogen at 2, calcium carbonate was 100, magnesium chloride 24, chlorine 35.5, added together because there were 2 of them. We get ourselves 35.5, which is 71, plus our 24, we get 95. So formula mass is quite easy. The rule, find your atomic mass in the periodic table, multiply the atomic mass by the number of elements you have, and add them together. Now, if the exam is going to be a little bit harder, I'm going to skip mole. We'll come back to moles later because that's quite rare to come up. They might ask you the percentage mass of our elements. Well, the principle remains the same. If I wanted to find out how much hydrogen there was in water, I've got a hydrogen element which weighs 1, but I've got 2 of them. And I've got an oxygen which weighs 16. So my total formula mass is 18. If I wanted to therefore find the percentage of hydrogen, well, in this particular case, I know that my hydrogen weighs 2, my whole molecule weighs 18. If I do 2 divided by 18 and multiply it by 100, my answer comes out at 11%. Now, at this point, let me give you a final top tip. If I was looking at that without my calculator, I'm saying I've got 2 of a total of 18. It's not quite, but it's pretty close to 2 of 20 or 1 of 10. So in my head, before I've done any difficult maths, I'm thinking I'm looking for an answer around about 10%. Again, it won't get any harder than this, but calcium carbonate, the same technique. Find the calcium in calcium carbonate. Well, calcium is 40, carbon is 12, oxygen is 16, but I've got 3 of them. If I then add them together, 16 times my 3 is 48, plus my 12 makes that 60, plus my 40 is 100. So I've got a total formula mass of 100. And if I'm looking for calcium, which I said had a formula mass of 40, 40 of 100. 40 divided by 100. If we're going to be really technical, we're going to do 40 divided by 100 times our 100%. So we will get 40%. Ladies and gentlemen, I'm going to leave you with this last point, empirical formula. Now, this is probably the thing that daunts people the most, but there's a couple of structures and a couple of ways that we can do that make it very simple. My first point, more than anything, is read the question. They are likely at GCSE to give us easy numbers and easy things to quantify. Empirical formula is essentially a way for us to say what is the simplest ratio of elements we have. It's like saying the following: we all know water's H2O, but how? Well, let's have a look. Find the empirical formula of the iron oxide produced when 44.8 grams of iron react with 19.2 of oxygen. How are we getting there? Well, let's have a look. The first thing we do is say, what are we reacting? Well, I've got myself some iron and I've got myself some oxygen. I know that I've got 44.8 grams of iron because they tell me it there. And I know that I've got 19.2 grams of oxygen because they tell me it there. The next part is to then find the atomic mass. Well, they give it to me in the exam, but if not, I could go back to my periodic table and I would find iron is 56 and oxygen is 16. Now, very quickly, I'm sorry guys, I'm going to quickly do it on a slightly bigger board so we can just see where we are, because I've got all the digits now that I need. Okay, the step is now very, very simple. You divide one by the other. So the 44.8 grams of iron divided by the AR of iron, 44.8 divided by 56 is 0.8. 19.2 divided by 16 is 1.2. In other words, for every 0.8 of iron, I get 1.2 of oxygen. Now that's quite a difficult number to comprehend, and we need to get it down to the simplest ratio. So you need to find out a number that goes into both the minimal amount of time. So I can't use 0.8 because 0.8 doesn't go into 1.2. And I can't use 0.6 because that doesn't go into 0.8 cleanly. The first number that goes into both is 0.4. It goes into 0.8 twice. It goes into 1.2 3 times. Now, you might find it at this stage to not actually look at that particular part, but to multiply by 10. Because multiplying by 10 makes the numbers so much simpler. I'm now saying I'm going from 8 to 12. And with that in mind, 8 to 12, what goes into 8 and what goes into 12 in its simplest ratio? Well, 4 does. 4 goes into 8 twice. 4 goes into 12 3 times. So what iron oxide have I made? I've made Fe2O3. I've made iron 2 oxide. One final example, ladies and gentlemen, and we will call it a day there for this session. Again, you might want to pause this and come back to. It's found that 207 grams of lead combined with oxygen to form 239 grams of lead oxide. I've no idea how much oxygen has been used. It hasn't told me. I need to find the formula of lead oxide. And they've given me my masses. Well, if we look back at our normal good science, we would know of the conservation of mass. Mass will remain. So in this example, if I have a look and say of my lead oxide, I've got myself 239 grams produced, and I started off with 207 of lead. The only thing in lead oxide is lead and oxygen. So 239 minus 207 gives me 32 grams of oxygen. And with that in mind, this is where I go. As before, I've got my lead, I've got my oxygen. I know I had 207 grams of lead. I know I had 32 grams of oxygen. I know that because that's what I've been formed with. If I then use my periodic table, I can find my AR, and it's a nice one because conveniently the AR of lead is 207. And on this, my AR of oxygen is 16. Well, we simply divide. So I get a ratio of 1 to 2. I don't need to do anything else with this. This is as simple as it will become. So my ratio, my formula would be PbO2. Ladies and gentlemen, that's all I'm going to do for this particular presentation. This has been recorded, so I'll show you this exam question number 5, and I'll show you this exam question number 6, that you might want to have a look at in your own time. And what we'll do is I'll go back to my very original slide. We haven't talked about moles, but everything else we have covered. So we've covered atoms, we've done new materials, we've done chemical calculations. Next time, I will do the analysis, I will do reaction, salts and electrolysis, and we will very quickly talk about moles. I hope you've enjoyed this. I hope you found this useful. I would really appreciate any feedback that you've got, be that the time of day, be that the way that the technology worked, if I've gone too quickly, if my writing is hideous and you can't understand it. But thank you very much for your time. I hope you've enjoyed it, and we'll see you for the next one. Thank you very much.